Yeah, I don't know if I can get on a skateboard like that, but somebody definitely did. This looks super dangerous. So, we're looking at third law, so let's kind of review the first two before we jump into it. So, Newton's first law was, object in motion stays in motion, object at rest stays at rest, unless acted upon by an outside force. The second law says F equals ma, force is mass times acceleration. And then we did a lab on that, and now we're talking about Newton's third law. So third law sounds the easiest, but it's one of the more interesting ones when you get into it. So third law states that for every action, there's an equal and opposite reaction. So here you can see, say the guy standing on the skateboard while firing the gun. The whole action-reaction thing is actually the firing of the gun. This being Texas, I'm so most of fire guns. But if you fired a gun before, you know that like you pull the trigger, the bullet firing out the end of the barrel, that might be the action force, the gun's pushing the bullet forward. Well, the reaction is the bullet will push the gun backwards. And if you've ever fired a gun, guns have recoil, they go back. Here, in the little picture you're just seeing him use the recoil to propel himself. The hardest part about Newton's third law is that the forces do not cancel. If you look at just an object, just say like that bowling ball we talked about before, the bowling ball is just sitting there, it's got gravity pulling it down, it's got the normal force pushing it up. So they're opposite forces and they happen to be the same size in that case. So a lot of people think that is Newton's third law. That is not Newton's third law. Those are two forces that just happen to be the same size, going in the opposite direction. Newton's third law, it's a third law force because it's an action-reaction pair. So another way of thinking about Newton's third law is that forces come in pairs. That means they're the same size, they're opposite direction. I think most people get that, but you also have to know that they act on different objects. The fact that the gravitational force and normal force are acting on the same object should indicate that's not a Newton's third law pair. So for example here, you can see like the picture up top shows like somebody pushing on the ground. Like that's an action force. You push on the ground. In this case, kind of down and back. And then the reaction force is the ground pushes you kind of up and forward. That's an action-reaction. But they're on different objects. One is on the ground, the other one's on you. Okay? So they're equal and opposite, but they act on different objects, which is key. Because they act on different objects, they cannot cancel. Right? Gravity can cancel the normal force, but the force on the ground does not cancel the force on you. So here's an example. It says we have two football players, Alex and Jason. They collide head on. They have the same mass and the same speed before the collision. Okay? They hit each other. How does the force on Alex compare to the force on Jason? Why do you think so? So first of all, what do you all think?
Well, shouldn't they be the same if they're the same size and running at each other at the same speed?
Yes. So they should be the same. All right. So they hit each other. We should have the same force. Everybody okay with that? All right. So now, suppose Alex has twice the mass of Jason. How would the forces compare? Be careful. What do y'all think? Alex is bigger. Twice as big. How do the forces compare?
Well, wouldn't it be half as big because Jason's got half the mass of Alex, and if he hit it, it should cancel out one half of it and the other half, or like half bigger. I don't know.
Okay, well, there's some good ideas. In reality, the forces are the same size because it's a third law pair. If Alex hits Jason, well then Jason hits Alex just as hard. Now the reason why it can be a struggle or it doesn't seem right is because Well, let's go ahead and look at the third one. It says Alex is twice the mass as Jason, but now Jason's not moving. Well, how do the forces compare? Well, the forces would be the same in this scenario as well. So if we look at the third scenario, the third one's a little bit easier to wrap your head around. Okay, Jason's just standing there and Alex just plows him over. If you've ever watched football, you'll see that happen. Not that often, but when it does, Jason gets lit up. But in that reaction there, you see, say Alex hit Jason that's just stationary. Well, Alex more or less keeps going forward when he hits Jason. And Jason, will start to move, let's say, backwards from our little picture. So when you see this happen, you go, oh, okay, well, Alex is bigger than Jason, and he moved Jason. So Alex's force must be bigger. No. That's not correct. The forces are the exact same size. The differences in their motion actually occur because they have different masses. Therefore, they end up with different accelerations. So when two objects are exactly the same, let's say they have the exact same speed, when they hit each other, they experience basically the exact same force, and you can see that, right? Like if a car hits another car and they're both the same size, they both get basically the same amount of damage. However, if you see a car hit something bigger than that car, like a big truck, does the truck end up with the same damage as the car? No. But the force is the same. But because the car has less mass than the truck, well, then the car actually gets a bigger acceleration than the truck, and therefore undergoes more damage than the truck. Does that make sense? So pretty much anytime you have two things hitting, the forces are always equal. Right? It's an action-reaction pair. But we see differences because of the differences in size of our objects. Does that make sense? So let's look at some more examples. So here's a bunch of examples. So we have action and reaction. So action, exhaust gases are pushed down out of a rocket. This is how rockets work. They take fuel, they burn it, and that exhaust gas is pushed out the back. This is different than the exhaust coming out of your car. Because literally the way a rocket works is that exhaust gas goes out the back. That's the action, it pushes gas out the back. The reaction is the rocket goes forward. And the reason why this is different is because this can work in outer space. Like your normal car engine would not work in outer space, okay? The jet engine would not work in outer space. So we have this action-reaction force. Now if you look at a rocket taking off, especially from like a launch pad, you might notice that the rocket doesn't start off going very fast. Well, that's because it has a lot of mass, and it's literally pushing out the fuel very fast, but the fuel doesn't have much mass, so it doesn't push back very hard. But again, same force, but different reactions. So same force on the rocket as on the fuel, but the fuel ends up going a lot faster than the rocket. Does that make sense? Because they have different accelerations. Where a sprinter pushes off the starting block versus a sprinter pushing upwards, or the block pushing upwards on the sprinter. A vase of flowers pushes down on the table when the table pushes up on the flowers. A tire rolling pushes back on the road, and the road pushes the tire forward. A ball that's hit by a bat, well, the reaction force would be that bat is then hit by the ball. Right? It's action and reaction. An orbiting satellite gets pulled towards the Earth, and the satellite, or the Earth gets pulled towards the satellite. Action, reaction. But again, the Earth is so big, it doesn't really move compared to the motion of the satellite. Right? The acceleration on the Earth is basically zero, and you really just see the satellite orbiting the Earth. And then the last example on this slide is, punching somebody in the face. If you punch somebody in the face, that's the action. Well, the reaction force is that their face hits your hand. So what I think is really interesting is if you look at this bottom picture here, of this guy getting punched in the face in slow motion, you can actually see several things going on. First of all, action, reaction, his fist hits his face, or bird face hits the fist. But if you look, you can see how his skin gets all twisted and distorted. That's actually because of Newton's first law. Because an object at rest stays at rest. So like, when he gets punched, his skull starts to move. It's a relatively solid object. But like the skin and the muscle and tissue on top doesn't really move at first. And so you'll notice, especially like his nose and his mouth, like lag behind the rest of his face. Because, well, they're objects at rest and they want to stay at rest until, you know, the rest of the skin just kind of drags them along. There's a couple of interesting things about boxing. I'm not going to get into all of them. But one of the interesting things about boxing is a lot of people think like, oh, if you wear these boxing gloves, it hurts less, right? Because there's really two types of boxing, if we're kind of going with just plain boxing, not like kickboxing or something. So there's boxing with gloves and boxing without. Right? What's interesting about boxing without gloves is it's actually less dangerous than boxing with gloves. A lot of people see the gloves and they go, well, you got this big, nice cushion here, and it makes it hurt less. It sort of makes it hurt less, but it actually just makes it hurt less on your hands. It still hurts to get punched in the head. And as a result, if you do bare knuckle boxing, there's less injuries in that, because it turns out when you punch somebody, it hurts your hand. And if you punch them really hard, it really hurts your hand. So in bare knuckle boxing, most of the time, people aren't punching as hard as they can because it hurts a lot more. But with regular boxing, it doesn't really hurt that much to punch somebody, so they actually punch harder most of the time, which is why more injuries and deaths have occurred in regular boxing than in bare knuckle boxing. So that's just a little tidbit of information for you. Fun fact, one of the first things you learn as a boxer is not how to punch, but rather how to take a punch. These next couple of slides talk about a hammer hitting a nail. When you look at a hammer hitting a nail, upon which is the force greater, the hammer or the nail? Not quite, not the hammer.
It should be the same.
It should be the same. They are the same. So first of all, they're all the same. The main reason for the difference is, well, which one's bigger, the hammer or the nail? Hammer. Therefore, with the same force, hammer doesn't do much acceleration. Actually, here you can see the hammer stop. And then the nail will accelerate forward. But again, the nail is smaller, therefore, it's going to have more acceleration. Now, there's a couple of questions. There's like one on this slide, and I think there's one on the next slide. And the question is, okay, when you hammer a nail into a board, how come it goes into the board? Because the nail is hitting the board. Well, the force between the nail and the board should be the same. Why does the nail go in? But again, force is the same, but the accelerations are not. The board's a lot bigger than the nail. Therefore, when you hit it, the nail will accelerate. And when it hits the board just doesn't move as much. Therefore, the nail goes faster than the board. Therefore, it gets drilled into the board. One of the biggest issues with rationalizing Newton's third law actually comes from a concept we're going to study soon called impulse. I'm not going to get into it right now because we'll get into it when we get there. But essentially, the things arise, like if you think about like taking this hammer and like swinging it, well, there's an action between your hand and the hammer, right? And then when you hit something with that hammer, there's another action-reaction pair between the hammer and the nail. And then there's a third action-reaction pair between the nail and the board. And the hammer, let's start with your hand. The force between your hand and the hammer is one set. And they have the same size force, opposite direction. But then the hammer hits the nail. That's another set. They have a different force, but they're equal to each other, opposite direction. And then you have the third set of where the nail goes into the board. Again, another pair, which are equal in size, opposite direction. But out of these three pairs of forces, none of them have to have the same force. Okay? Just the forces have to be equal to each other in that pair. But for instance, when you swing a hammer, the force you use is pretty small compared to the force that gets delivered to the nail. And the main reason for that difference is time. I mean, when you think about it, if you've ever hammered something? If not, I got a hammer in there you can use. if you hammer something, you have this whole swing, and if you time, the time it takes to swing, let's say it takes maybe a second to swing, okay, bang. But the time where the nail is actually being hit by the hammer is incredibly short, much less than a second. As a result, the force tends to be very high. And so that's kind of what's going on here with these different interactions, is that every single collision between two objects ends up with the exact same force. And you guys got to know that. When I give you questions on the third law, I'm going to be like, hammer hits a nail, which is the force bigger? They're the same size. I'm going to say, car hits a truck, which one is the force bigger? They're the same size. Okay? You got to know that now, because when we get to impulse, we're going to use that, and we're going to say, okay, the forces are the same, the times are the same, how come the car gets destroyed? Well, because the car has a bigger acceleration than, say, the truck. Alright. So here, again, it's still talking about this. I'm not going through this one in particular since we talked about it right there. Let's talk about this guy here. So this is a good, overall example of not just third law, but just general problem. So here, what we're going to do is, it's got a sort of a free body diagram there, but I'm going to go ahead and draw a different one on top of that so we can do this. All right. So it says we have two horizontal forces, 225 newtons and 165 newtons are exerted in opposite directions on a crate with a mass of 5 kilograms. Then it asks us to find the net horizontal force, the net vertical force, and the acceleration of the crate. So to do this, the first thing we're going to do is draw a free body diagram. Let's draw a better one than that. So when we do this here, so there's my dot that represents my object. So let me draw the forces on it. So what forces are acting on this crate? Gravity. What direction is gravity? Down. Down. So I'll draw this one down, right? Force of gravity. Anything else?
Someone's pushing up on the crate.
And the normal force can be pushing up on the crate. It's really off my dot, but whatever. Okay. And since we're assuming this crate is sitting on the ground on Earth, those two should be the same size. Everybody okay with that? What other forces are acting on this crate? I can see two right here. So it says we have two horizontal forces acting on the crate. Now it doesn't tell us which direction the forces are in. So I'm just going to kind of stick with what this picture has here. It doesn't say what direction, it just says they're both horizontal and they're in opposite directions. So, I can stick with the picture here and I can say, okay, this is my 225. And then this one back over here, be sure to draw it smaller, 165. Right, and that's what we start with. Everybody okay with that? Yeah. So whenever we have forces or vectors in opposite directions, we need to label those directions as positive or negative. So for example, we could call like up positive, and therefore down would be negative. And in keeping with this problem here, I'm going to call the right positive, so the left ends up being negative. It's important to note because if you look at this picture, it just says negative 165. I want you guys to know where this negative number came from. This is 225 and 165 in opposite directions. So you're going to end up subtracting them. And really, it doesn't tell us which one's going in which direction, so you can call either one positive or negative. Just in general, we're going to call the bigger one positive, so when we do subtract, we don't get negative numbers. Are we okay with that? Okay, so we drew a free body diagram, we labeled all of our forces. Now, let's find the net horizontal force on the crate. So the net horizontal force, I would actually write as F net, but it wants horizontal. So I'm just going to write X for horizontal stuff, right? And we'll write, Y for vertical. Well, that means we only have to look at our horizontal forces right now. Well, horizontally, we have 225 and 165. So let's just add those together to find the net force. So we do 225 newtons plus our negative 165 newtons. And that will give us our net force, F net, but only in the X direction, right? Only in the horizontal direction. Well, it's 225 minus 165. Yeah, 60 newtons. Okay. I'm very clear on where we got this 60 from. So that's the answer to our first question there, right? The net horizontal force. Everybody okay with that? Okay. Now let's go to the second question. It says, what's the net vertical force? Well, the net vertical force is just going to be adding the two forces going up and down. So for this one, I'm going to say F net, but in the Y direction. So in this case, it will be the normal in gravity. So I call them normal positives, therefore gravity ends up being negative. Now, we know how to calculate the force of gravity, right? Force of gravity is simply mass times the acceleration of gravity. Or in this case, 5 kilograms times 10, which is where these 50s come from in our picture. But here's the deal. I'm not even going to calculate that because we don't need to, because it asks us to find the net vertical force. Well, if you're shoving a crate along the floor, is it flying up into the air? Is it going down through the floor? No. So what is the net vertical force? 0. And that's the only reason why we know the normal, because it has to be the same as gravity, just opposite direction. So the net force in the Y direction has to be 0, because it probably is going to be 0 a lot of the times. Unless it says, okay, you're throwing this rock up, or you're launching a rocket up. Net force in the Y direction is probably going to be 0. Not all the time, obviously. But, just shoving something along the floor, it's going to be 0. And now it wants us to find the acceleration of the crate. Okay. So, that's not too difficult, but before we get there, I do want to cover something here. This says you have two horizontal forces, 225 and 165, exerted in opposite directions. At first, if you're just like, okay, that's fine. We have a box and maybe two dudes just pushing on it. But then we stop and think about it, like, if you had a box that's too heavy for you to move and you had somebody help you with it, would you both be pushing in opposite directions?
No, one would be pulling.
Yeah, well, if they're pulling, well then, if one's pulling, one's pushing, they should still be in the same direction, right? So, this is a very weird question. Like, a lot of students will just chalk it up and be like, oh, whatever, just stupid teacher asks a stupid problem. Maybe. But, I want you guys to realize that if you are pushing a box, you probably don't have somebody assisting you by going the opposite direction. What I want to point out here is actually what we're going to see in the next set of the notes, is that, let's say you're pushing this crate. Well, what pushes against you? What makes you not go as fast? Friction. So this is probably friction between the crate and the ground. Does that make sense? So I want to kind of just make sure to point this out, that this is, in a typical problem, this would probably just be called friction because it opposes, the motion you're trying to apply to it. But we didn't call it friction at this point. We just said two horizontal forces. I mean, you can imagine it's two people, but I'm sorry if I ask you to help and you're pushing the opposite direction, you're not much help. All right, so let's go ahead and find this acceleration here. So to find the acceleration, we have to find just the total net force. Because our acceleration, F net, is simply mass times acceleration, right? So if we know the net force, we know the mass of the crate already. So we just take that net force and divide by 5. Now, in this case, it gave us a net force of 60 for the X and 0 for the Y. You might have 0 for one of them, and for y'all, a lot of times, at least one, if not both, of these are gonna be 0, okay? But what if they're not 0, okay? So what I'm gonna do right now is I'm gonna show you how to add these two together, regardless if they're 0 or not. Obviously, if one's 0, it's gonna be really easy. But when I show you this, you should notice that it's not new. You already know. If I wanted to add these two together to find the net force, let's say I want to find just the total net force, so net, not an x or y. Well, what I would do is I would take F net x, and I would square it, and I'll add to that F net y, and I would square that, and really that would not give me the answer, that would give me the answer squared, right? What is this? Where something squared equals something squared equals something squared?
Pythagorean theorem.
Pythagorean theorem, right? Because these are vectors, and literally like the x direction would go this way, the y direction maybe goes that way, and so the net would be, well, the other side of your triangle. Okay. So first of all, this is just Pythagorean theorem, is how you would add them together. Second of all, if one of them 0, what's 0 squared? 0, so like this term is gone. So this squared equals that squared, well, it's going to be the same number. You all see that? Because we're not adding anything to it, we're adding 0. So in this case, my net force is simply the net force in the x direction, because y is nothing. So my net force is 60. Everybody okay with that? So it's 60 because, well, x is 60 and y is 0. So I can plug that in here. I can say, okay, we got 60 newtons of force equals the mass, which is 5 kilograms, times acceleration. Well, opposite of multiplication is division, so I'll divide by 5 kilograms. So what's 60 divided by 5? 12 meters per second squared. You don't know that? Get a calculator. And so that's our answer. That's our acceleration. So in the end, there's only one crate, so there can only be one acceleration. We can look at these things individually, and the reason why this problem asks you to find net force horizontal, net force vertical, is not because I wanted to ask you 3 questions, but in order to solve the acceleration of the whole object, that should be your steps along the way. You should find the net x, find the net y, and if one of them's 0, that makes things a lot easier. All right? Now, like I said, most of the time for y'all's problems, to keep it simple, one of the two, either y or x, will be 0. Therefore, your net force is just simply the forces in that particular direction. All right, is everybody okay with that? Okay. So, go to the next slide. So these last 2 slides here talk about friction, which I just mentioned. And we've mentioned a couple of times. Remember, friction opposes motion. Now, there can be several different types of calculations when it comes to friction. So especially if you're going to look up stuff online, you need to be very careful, because we're taking friction at the lowest possible level. Okay? Like, yes, friction happens. But if you start to look up stuff about friction, you'll see a whole bunch of like coefficients and all these mu symbols. That's all good stuff, and if you understand it, great. But we're not going that far, okay? We're just looking at the basic concepts of friction, like why it occurs, and how you're going to interact with it. Now, again, there are 2 types of friction. There's static friction and kinetic friction. Static friction occurs when you push on an object, but it doesn't move. And kinetic friction occurs when one object slides on top of another one. So the way you kind of explain this is if you take your fists, and you take your hands to make fists, if you put the knuckles of your fists together like this, you'll notice that they kind of move, right? Like they can kind of interlock. When they're interlocked, that's like static friction, right? And then if you just kind of run your knuckles on top of each other, that's kinetic friction, okay? So there's a couple of things in that analogy here. So the first thing that you should notice is that when your knuckles get interlocked, why would that happen? So that even happens on 2 relatively smooth surfaces, okay? Because everything is made up of atoms, and atoms, by definition, are not smooth. So, you know, basically, when you get down close enough, your two objects will not be completely smooth on each other. Does that make sense?
Yeah.
So there's always going to be some friction. Obviously, the smoother the object, the less friction there should be. The other thing you should notice is that it's easier to run your knuckles just like right on top of each other than to get them out of the hole. Okay? And so static friction is trying to get these things up out of the hole, and kinetic is just when they're sliding on top of each other. So static is always going to be bigger than kinetic, right? Yeah. And so these two forces here, you can kind of think of, like here it shows you pushing a jug of orange juice or something, but if you think about something a little bit bigger, like say a dresser, or maybe a bed or a couch at your house, if you've ever tried to move one of these objects and it didn't move, let's say you go to push on the dresser, and you're like, "Ugh," and it doesn't move. Okay, well then, let's say you just, pull up the pants, and then you just push harder, okay? And let's say the second time, oh, it finally just moves. But what's interesting is, does it just move easily after that? No. You end up moving it like little random like bursts, right? Like you're pushing, it's like jump, jump, jump. Because what's ending up happening there is that you push hard enough to overcome static friction, and then it starts to slide. But it only slides, well, basically to the end of your arms, right? As far as you can reach. Then you're not applying force anymore, so it slows down and stops, and then you have to do it again. So the basic differences between static and kinetic, and remember that static is always going to be bigger than kinetic, all right? So here, this slide talks about static, and then this one talks about kinetic. But they do have something in common. They're caused by two objects being in contact, and whichever friction you're talking about, it's going the opposite of the direction you're trying to push it. And so on the last slide there was a little video about friction, which I encourage you all to watch to learn a bit more. So are there any other questions about these notes? Okay, well that's the end of the notes then.